All right, so we conducted our simulation study so that we could evaluate the performance of this sort of new two-step approach and compare that to the conventional Eggers test. And we also wanted to look at comparing the performance between these sort of different measures of study size. So obviously, Eggers test uses standard error, but we also wanted to look at what happens when you use sample size or inverse sample size as well. So we looked at 4 scenarios across 2 settings. So the 2 settings were 30 trials for every meta-analysis, and the second setting looked at 15 trials in a meta-analysis. And then our 4 different scenarios, we looked at different combinations of the baseline risk interaction and publication bias being present. So we started with neither present, and then we looked at one without the other in both cases, and then we looked at what happened when both baseline risk interaction and publication bias were present. So in terms of generating our data, when there was no baseline risk interaction, we simulated our data for an individual 2-arm trial with a continuous outcome, assuming the responses for each patient were normally distributed. Here the mean μc is our underlying average response in the control group, and sigma here would be the standard deviation of the responses in the trial. In the treatment arm, we also assumed that the responses were normally distributed, but this time with a treatment effect. So treat.diff here is our intervention effect. So in the patients in the treatment arm, the mean is equal to the mean response in the control arm plus the intervention effect. And again, we had the same variance as we did in the control arm. But when baseline risk was present in the control arm, then we assume that the standard deviation depends on the mean response in the control arm. So we're still simulating from a normal distribution with the mean response μc, but now the standard deviation also depends on μc. And in the treatment arm, we have both the standard deviation and the mean response depending on the mean response in the control arm. So here our mean is the mean response in the control arm plus our intervention effect. And then here this B dot interaction term represents the strength of the baseline risk by treatment effect interaction that we have. And once again, the standard deviation also depends on that response from the control group. So across both slides here, the variance in the control and the treatment arms is the same. So by doing this, we assume that both treatment arms are influenced by baseline risk in the same way. Treat.diff, we have this constant across trials within a meta-analysis, so that other than the effect of baseline risk on treatment effect, we're assuming homogeneity of the treatment effects across all studies in each meta-analysis. And again, across both slides, the normal distributions that we've generated from these were truncated at 0 to ensure that the response could not go negative. So if we're thinking back to the morphine consumption example, you can't have a negative morphine consumption. So by truncating the distributions at 0, this prevented that from happening. And so then to induce the publication bias, once we'd generated the control and treatment arms, we were able to calculate the mean difference and the variance for every trial. And from that, we got our two-sided Z statistic and our p-value. And if that p-value was greater than 0.05, we excluded the trial from the meta-analysis, and we continued to generate further trials until we had our pre-specified number of trials, so either 30 or 15. We considered 6 methods. So method 1 here is Eggers test, where we do the regression test on the observed data using standard error as the predictor. And in methods 3 and 5, again, we use the observed data, but we look at sample size and inverse sample size as the predictors. In methods 2, 4, and 6, we conduct this is our new approach where we first do our meta-regression, adjusting for baseline risk interaction, and then we conduct our regression test on the residuals, and we looked at standard error, sample size, and inverse sample size as the predictor. So our estimand was the proportion of times that the p-value for the funnel plot asymmetry test was less than or equal to 0.05. We simulated 10,000 meta-analyses per scenario, and the mean response in our control arm took one of these values from the range of 20 to 50, whilst trial arm size took one of the values of either 15, 25, or 50 patients. And within a simulated meta-analysis data set, our mean response in the control arm and the trial arm size were the same for each trial, and we assumed that patients were randomized in a 1-to-1 ratio between the control and treatment arms. And we did our data analysis using the meta4 package in R. Okay, so this table shows the results from the first 4 scenarios where we had 30 trials in each meta-analysis. So here the rows correspond 1 to each of the 4 scenarios, and the columns 1 to each of the 6 methods that we considered. So over here on the left, the first 2 columns look at using standard error as the predictor, firstly with the observed data, and secondly with the residuals after adjusting for baseline risk interaction. And then in the middle, we're looking at sample size, and over on the right-hand side, we've got inverse sample size. So if we consider scenario 1, where we had no baseline risk interaction and no publication bias, then all 6 approaches to testing have produced a similar result for the funnel plot asymmetry, showing that it was significant approximately 5% of the time. And that is sort of as we would expect to see sort of by chance alone. So all 6 methods here are behaving in the way that we would have expected. In scenario 2 here, where we have a baseline risk interaction present, but there is no publication bias, then we can see that Egger's test has incorrectly identified funnel plot asymmetry 60% of the time. And if we were to, with our observed data, if we were to use sample size or inverse sample size, then we see that that reduces down to approximately 1% of the time. If we switch to the new approach, but still use standard error, then we're seeing the funnel plot asymmetry sort of identified 8% of the time. But if we use sample size or inverse sample size, then we're seeing results about 5 to 6% of the time, which is in line again with that sort of 5% that we would expect by chance. In scenario 3, there's no baseline risk interaction now, but we do have publication bias. And what we can see is that all 6 methods are correctly identifying publication bias approximately 60% of the time. So now we see that in scenarios 1 and scenario 3, where in both cases there's no baseline risk interaction, the 6 methods all work, have sort of comparable results and seem to work in the same way. But if we look at scenario 4, where we've got both baseline risk interaction and publication bias present, then we see that Egger's test identifies the funnel plot asymmetry 99% of the time. We think this needs to be viewed in the context that in scenario 2, where only baseline risk was present, it was already identifying asymmetry 60% of the time anyway. If we were to switch to using sample size or inverse sample size with the observed data, then we'd identify this funnel plot asymmetry about 35%, 33% of the time. But if we use our new approach and we adjust first for baseline risk interaction, then when we use standard error, we're only identifying asymmetry less than 1% of the time. However, using sample size or inverse sample size, then we sort of identify this asymmetry 36% and 40% of the time. So this table now is the results from where we had 15 trials for each meta-analysis. So the first thing to say is that the results generally were very similar to when we had 30 trials for each meta-analysis. So that in scenario 5, where we've got no baseline risk and no publication bias, all 6 methods are performing pretty much comparably to each other and identifying asymmetry that 5% of the time that we expect by chance. In scenario 7 here, again, where we've got no baseline risk interaction, but we do have publication bias now, we see that Egger's test is identifying that publication bias 31% of the time, and this is a reduction from 60% when we had 30 trials in each meta-analysis. In scenario 6, where we've got baseline risk but no publication bias, we can see that Egger's test is incorrectly identifying funnel plot asymmetry 39% of the time, which again is a reduction from 60% when we have 30 trials. But when we have both baseline risk and publication bias, using the new approach with either sample size or inverse sample size, then we're identifying asymmetry sort of 15% and 16% of the time, and this is reduced from 36 to 40% that we had when we had 30 trials. So this slide here contains funnel plots from the first 4 simulated meta-analysis data sets for each scenario. So these are pairs of plots. So these 2 plots here are the same data set, but on this blue plot on the left, this is our new approach where we've got residuals on the x-axis and inverse sample size on the y-axis. And this red plot is Egger's test, where we've got mean difference on the x-axis and standard error on the y-axis. And what we've plotted on these ones, we've plotted the regression lines from the associated regression tests. So so these 2 plots here are from the first data set that was generated for scenario 1. These 2 are from the second data set for scenario 2, and so on, with each row representing the 4 different scenarios. So what we see in scenario 1 here and scenario 3 is that our blue and red plots here are, the regression lines are fairly comparable to each other between the methods. So this was when baseline risk was not present, and we see that the sort of 2 methods are fairly similar. But in scenario 2 here, where we had a baseline risk interaction but not publication bias, then what we can see is sort of the superior performance of the new approach, where the regression lines are much closer to the vertical with our new approach than they are in Egger's test. So here we're sort of correctly implying that there's sort of little or no asymmetry. And in scenario 4 down here, what we see is sort of a lack of strong trend in our residual based plots, sort of reflecting the diminished power of our residual based test when both publication bias and baseline risk interaction are present. Okay, so we've covered quite a bit so far, so I'm just going to sort of summarize where we've got to. So meta-analyses are frequently used for informing clinical decision making and guidelines, And so therefore, if we're using sort of invalid data, then this could lead to the use of ineffective or harmful interventions in clinical practice. So it's important that we assess our meta-analyses for evidence of publication bias, and the presence of publication bias can lead to the downgrading of the certainty of evidence using the grade approach. To date, most of the work has focused on binary outcomes, but it's important that we also have appropriate methods for identifying publication bias using continuous outcomes. And due to the fact that in the presence of baseline risk, then meta-analyses of continuous outcomes can exhibit considerable heterogeneity, it's also important that we can take into account that baseline risk when we use our methods for identifying publication bias. So we noted that in the field of post-operative pain, studies with sort of a higher control group morphine consumption tended to have larger standard deviations, and this sort of led to this dependency between the mean difference and the standard errors, with both being larger with higher baseline risk. And through the simulation study, we showed that this can result in asymmetric funnel plots, even in the absence of publication bias, such as in scenario 2, where Egger's test incorrectly identified 60% of meta-analyses as having asymmetry. So to try and work around some of these restrictions, we've proposed a new two-stage approach in which we first adjust for this baseline risk interaction through a meta-regression. And in the second stage, we're performing the regression test on those residuals from the meta-regression, having accounted for baseline risk. And we recommend using sample size or inverse sample size as the predictor. The simulation study that we conducted allowed us to compare this new approach with the conventional Egger's test. And we found that our new approach performs similarly to the conventional methods when baseline risk interaction is not present, but it can reduce the type 1 errors in the presence of a baseline risk interaction when there's no publication bias, but that there's low power for detecting publication bias in the presence of both baseline risk and publication bias when we have 30 or less studies. And we did find that the performance of inverse sample size was marginally better than sample size itself. So I'm just going to hand back over to Alex, who's just going to cover a couple of the sort of limitations of our study.
Okay, thanks, Suzanne, again. If anyone's got questions, although I've only got a couple of slides here, so we may well wait, I think. So just to be complete, as open as we can about this, Brett found this data from previously published reviews, if you like, a review of reviews. So there may be some true publication bias here, i.e. and stuff not retrieved actually that is in the literature. We can't deny that might be a problem. One limitation of the simulation that Suzanne presented is that we didn't add in unexplainable heterogeneity on top of the heterogeneity caused by interaction with baseline risk of treatment. In the simulations I've done in the past in these sort of scenarios, that only really adds noise on top, and I don't think it's a major limitation, but until you do it, I can't say that for certain. Our prediction is that it would just lower the power things even more. So what we're seeing in terms of power percentages in Suzanne's results are probably best case scenario. You add a bit of unexplained heterogeneity on top of that and things will probably reduce further. So that means, you know, we think we've got something that works, but as somebody pointed out in the question, you will need quite a lot of studies. Something I should say as well, I'd like to say, is that this paper got some extensive peer review comments, and one peer reviewer in particular was very patient with us, made some very good comments, and over a couple of revisions, their insights really improved the paper. And I have no idea who that person is, but I'd like to thank them. And if they're listening, if they happen to be on this call and would like to identify themselves, I'd be delighted to thank them in person. And something that was pointed out is that we could actually do this in what we're saying a one-stage approach. We could do a regression, adjusting simultaneously for baseline risk interactions, and then testing the asymmetry. And while this is sort of statistically neat, the reason we didn't go for that primarily is because you can't then get the residuals out, which are sort of halfway along the analysis. You can't see what the funnel looks like after you've taken the baseline risk effect out. So we didn't pursue that. The third point here, I'm actually not going to talk about because it's very technical. I'm happy to talk offline with anyone about that. It's about how we think the error is in after you've fitted things. So traditional funnel plots are not reliable for detecting asymmetry effects for morphine consumptions. And we've shown that, and we found a way to overcome it. And for mean difference outcomes in general, we're recommending first accounting for baseline risk in meta-regression, and then assess the funnel symmetry by regressing residuals on inverse sample size. And present the results using a funnel plot with inverse sample size and residuals. That's basically the take-home message. But I think a message is important from this paper, for me certainly, is that we probably need to think a bit more carefully about when we're doing analysis of continuous outcomes. I think for meta-analysis, they've been a poor relation to binary outcomes, certainly in medicine. Continuous outcomes are very common in education and other fields. But they are common in medicine, and there's some very big data sets that use them. We've seen this one here, depression is another example. And there are quite a few examples in the literature where it seems that this sort of relationship exists and is strong, this interaction with baseline risk. The higher the propensity to reduce something, the more effective a treatment can look. So in a sense, I think there's a message as well that, as well as just looking for publication bias's sake, I think generally we may not be using the right outcome measure. Or at least we should be mindful that if we are using an absolute difference, the mean difference, which is what's used by default, we should think whether there is an interaction and whether we have to fit a more complicated model. And this leads on to saying that I think more research is needed for other continuous outcomes. Something that's had some proponents in the literature but hasn't got widespread recognition is using the ratio of means. Of course, for binary outcomes, we use odds ratios, relative risks, more commonly than risk differences in mesh analysis, and the reasons for that for stability. We don't really, it seems that we defaulted to absolute differences, mean differences for continuous, and we don't use things like ratio of means. There are problems similar to that of Krista's question, when that is actually true, when an outcome can go negative. Ratios are a bit of a nightmare to deal with, so there are limitations, but it's something I think is worth looking at. And indeed, Suzanne has a personal fellowship with part of her work. We'll be looking at this in some more detail. Okay, that's quite enough from me, so I'll shut up and let people have a chance to ask questions.